Now I will introduce some of the Calc 3 material that we cover in Calculus 2 so that when you get to Calc 3, you are prepared to hit the ground running. And a lot of this, though, we have seen. So the topic that I will discuss is vectors. We have seen, in particular, we had, when you have a particle moving around in space, we calculated the displacement and the distance traveled. We not only, for instance, the particle was a vector, or its location, I should say, is a vector, and then we could take the derivative, right? We have velocity, and then we did things like we found the length of velocity and integrated. It gave us distance traveled. Or we would just integrate the velocity function itself, if that's what you start with, and you could calculate displacement, which was a vector. Okay, so some of the notions of vectors we are familiar with, but I will sort of start from the beginning and solidify some other concepts. Okay, so let's talk about the important things about a vector and how that differs from some other things. So first of all, a vector, this has a direction and a magnitude. Or another way to say magnitude is length, okay? This is what gives you a vector. You have a direction and you have a length. Now this is different from a scalar, which is another word or concept that comes up quite often. A scalar is just a number, and this has no direction. Now, one example of a scalar that's sort of related to a vector, an example is the length of a vector or magnitude. This is a scalar, but a scalar in and of itself has no direction, whereas a vector has direction and length. And let's start with an example that we can think about, and this picture will have both a scalar and a vector. Let's take a box, and I'm just going to push this box down diagonally to here, and it ends here. Now, I have moved the box. Maybe I'll start at the center, and this went here. And let's say this is 2 feet, for example. Well, in this picture, we see both vectors and scalars. For example, the vector in this picture, so this is an example to think about these notions. The vector in this picture is this red arrow, and the scalar in the picture is 2 feet. This is, oh, maybe I should give a little more space, excuse me. The scalar in the picture is 2 feet. This is, well, for instance, it's the distance that it traveled, or it's the length of the vector. It's, maybe I'll put a bullet, or it's bullet, it's the distance the box was pushed. Box traveled like this. This vector, though, the red vector, the arrow in my picture, is the displacement of the box. And this should not be too surprising of you, given, as I mentioned at the beginning, that we have studied displacement. And in this case, I'm in a two-dimensional picture, kind of, but it would be a vector which would have 2 components. Okay, it's an arrow. Now, one thing that I want you to, there's sort of 2 worlds in the vector world. There's the world of the algebra, which was most of what we did. Well, of course, we had calculus, but where you work with components, and I will get to that. But what I will start is the world of things like this, which is arrows. And so I really want you to think about, maybe I will erase this part to make my comment. I really want you to think about vectors as being arrows. Okay, this is sort of a geometric way to think about them and is quite helpful quite often. Okay, so every time you see or think about a vector in Rn, think about an arrow in Rn. Now, let's say we have 2 points, and the points, I'm going to get to this picture, which is an R2, but when I am drawing arrows, even though I'm drawing them on a plane of this whiteboard, they could really be in any n-dimensional space. Let's say we have point P and we have point Q. And as I mentioned, these could be sitting in some n-dimensional space. Then this vector PQ, this notation, this has, let's see, tail P and head Q, and it would look like this. You have some point P in n-dimensional space. You have some point Q in n-dimensional space, and this is the tail, and then this is the head, and it points like this. Now, let's discuss when our 2 vectors equal. And this is quite an important comment or observation. 2 vectors, let's say V and W. Well, let's see. Before I get into when are they equal, let me just get a little bit about the notation. And we certainly see this on the board. Here I have drawn 2 vectors, and we will discuss those momentarily. But this notation with a hat, or you might even see being an arrow, this we have seen when we were doing position P of t. There was a little hat over the P of t. It's very common when you're dealing with a vector, not a scalar, to put one of these or put a little arrow on top. Other times you will see this notation where instead of a hat, you see this very, very bold face like this for a vector. As opposed to a scalar, which would either not have a hat or would not be bold face like this. When I'm writing on the board, I will put hats on things because it's easier than shading super heavy to make it look bold. Okay, so now 2 vectors, V and W, these are equal. Provided, well, let's go back, and I have erased it. What is a vector? A vector is a length or a magnitude and a direction. So they're equal provided they have the same length and the same direction. Okay, so in particular, this example over here, and I like this because it makes us think about this definition immediately. In this example, what do we see? We see that V1 equals V2, and maybe I should have done the equals in blue, for example. V1 is red, V2 is black, V1 equals V2, even though they don't occupy the same physical space. Or same physical space or location like this. So I have them drawn differently in the plane, but these 2 are equal. Now, how would you see that from the picture? Here, V2, it starts at the point 1, 0 and ends at 4, 1. V1 has tail or starts at, let's see, 1, 2, 3, 0 and ends at 3, 4. Now, I will get to the coordinate part momentarily or in a few minutes. Right now I'm only thinking of vectors as arrows. How could you see these 2 are equal from this? Well, you can move this over and up, and they will overlap on top of each other. So the length, which I'm thinking about, is literally the length of this arrow here, and the direction being the same would be because I could take one, pick it up, and not rotate it. Not rotating it would of course be different direction, but just do a shift either horizontally or vertically, and you would land on top of v2. These two vectors are equal. Let me mention briefly about the zero vector. The zero vector, it's this, or if you're using this boldface notation, it looks like this. This has 0 length. And I will mention that our text says it has every direction. And this is a convention of our text that can be useful in things that come in the future. Some texts, I will mention, say no direction. But in any case, the zero vector is the only vector with 0 length. And in any case, it's denoted like this. Now, what I want to discuss now is vector addition. You might be wondering, where are the components? The only time I really talked about components was when right here I had 2 vectors in the plane, and as I drew them, they had a different head and tail, but they were equal. Well, I really want to begin our discussion of vectors thinking only about arrows. Then I will get into the components and work with the algebra, which you probably have seen or feel more comfortable with just because of the work we've done in class. Okay, so let's say I have 2 vectors, v and w, and again, I'm thinking arrows. And what I want is a sum, v plus w. Okay, so how am I going to add 2 arrows and get an arrow? Well, there's 2 ways to do it. Okay, so way number 1 is called the triangle rule. And way number 2 is called the parallelogram rule, and they generate the exact same thing, but I will mention them both. And then I will talk about scalar multiple, and I will talk about subtracting 2 vectors. Okay, so the triangle rule. What you're going to do here, maybe I will write, is you place, let's see, you place the tail of W at the head of V, and then you connect. Well, we will connect the tail of V to the head of W. Well, this is a lot of words. It's much clearer in a picture. Let's say this is V. Now I need a W. It's going to be maybe green. Okay, so I take the tail of W and I place it at the head of V like this, and then I connect. So here's W, and then I connect, maybe in red, I connect the tail of V to the head of W here. Okay, except my line wasn't so straight. I am recording at home, and I don't have a ruler here, but I found this little Lego ladder that came off some Lego set. I can kind of make a straight line with a ladder. Okay. This is V plus W, like this. It's this red arrow. This is how we add using the triangle rule. Now the parallelogram rule, well, there's a little bit of a requirement here. We need that V and W are not parallel. Now I haven't yet defined that. I will momentarily, but you can think parallel lines. And then I will define parallel vectors once I define scalar multiple. Okay, so we need this, and then what you do is you connect the tails of V and W, and then the vectors form the sides of a parallelogram. Okay, maybe that's all I'll say at the moment. I will do it, and then we will try to, we'll see the parallelogram rule. So my V, I'm trying to draw the same one, went kind of like this. V, maybe a little longer. Okay, that's approximately the same V. Now instead of putting W here down, I just connect the tails. So W is going to come here. Something like this. Okay, this is W. And now these two, the two vectors, as is written in blue, form the sides of a parallelogram. This side would be here, and this side would be here. And now we just connect from the two tails, say I did that in red, here, to this side. This is V plus W, like this. Okay? Which, if I had actually drawn my vectors to be the same, I made mine a little shorter, you would see that V plus W would be the same in both situations. In fact, you can kind of see here the triangle rule goes from this side to this side. But in any case, there are two different rules that we can think about: vector addition, and we get the same thing. What I want to do now is scalar multiplication, which means I take C, a scalar, I take V, a vector, and what I want to produce is a vector CV, and this I'll say is the vector with, well, C can be any real number. I need to tell you a length, I need to tell you a direction, okay? And then I will have a vector, right? So this is a vector with length. Well, let's back up for a moment. I'll put it here, recall. This we have done, and I will do more of when we get to our, just momentarily when I start doing components. But this is notation for the magnitude or the length of vector V. And when I've been writing arrows in the plane, it is literally the physical distance or the length of that arrow, okay? So this is a vector, well, with length, absolute value of C times the length of V. So this is absolute value, okay, and this is the length of V. Well, now I've told you the length, and in particular, you see if C is 0, then we automatically get the 0 vector, okay? But the vector with 1, this is the length, and 2, I need to tell you a direction, right? So 2 is direction, and this is the same direction. I'll do it this way. Of V if C is bigger than 0, and it's the opposite direction of V if C is less than 0. So for example, if we took, let me draw a picture, and then again, if C equals 0, you can think about CV, well, it's a 0 vector, it has every direction, or some text you would say no direction. In any case, this part I'm really thinking about what's the direction if you have a non-zero scalar. So if I took this as V, and this will illustrate what I mean by opposite direction, well, what's minus V? Well, I keep the same length, which that might be difficult to do. It is a little bit longer than an eraser, and I go in the opposite direction, meaning I just go this way, okay? So this would go here. Like this a little bit longer than an eraser, like this. This would be minus v, for example, okay? And then another thing we can think about, let's say c is, for example, 5, or this idea would work for any positive integer c. Well, let's try and do the same v. You would just take v and v, 2, 3, 4, 5. This would be, if this is little bitty v, this big vector here, starting here, this is 5v. What we did, we kept the exact same direction, and we increased the length by 5 times, but also you can think about that in terms of this algebra that you're used to. We could just add, and I need one more, like this, we would get 5v. So there's 2 different ways of thinking about it when your scalar is a positive integer. One more thing I will mention with the arrows, then we will get into some component stuff, the algebra of vectors, and that is vector subtraction. Oops. I think we are okay. So subtraction, we did addition, scalar multiplication, subtraction. Well, if you want v minus w, this is defined to be the only thing that makes sense, which is v plus minus 1 times w, right? So in a picture, if we have, let's say this is v, and I don't know, maybe, oh, excuse me, this is supposed to be v. I wrote w. This is v, and maybe this is w, okay? So what I want is v plus minus w. Well, the first thing to do is draw minus w, which has the same length but points in the opposite direction. That would go here. Okay, this is minus w. And the way I have this set up is very natural to do parallelogram rule. So I would do this. And then we have this. And now we see the vector v minus w, uh-oh, I already used blue, I'll do it in red, is this vector here. This is v minus w, like this. And then definition, we say two non-zero, or we have two non-zero vectors are parallel This is what I'm defining, and I mentioned this earlier, but we will define it now. If they are scalar multiples, I'll say if they are each scalar multiples of the other. Okay, and then we will typically think about the zero vector as being parallel to every other vector, but this is really the definition for non-zero vectors, is that they're scalar multiples of each other. Okay, so this was fun with arrows, but now let's talk about components, and we will do some examples with components. So now I'm going to switch gears and discuss some of the algebra. Okay, so I'm going to start. So everything I have done really has worked in any dimension, because as I mentioned, you could think about your arrows as being anywhere. I'm going to start working in R2, and everything that I say in terms of the algebra extends to higher dimensions. I will just start with R2. Okay, so if you have P and Q, these are points in R2. Maybe I will even give them some coordinates. I'll erase this first. So P are points and Q, P is say x1, y1, and Q is say x2, y2. Then this vector, which we started with two examples down here, this is, well, we know it has head Q, tail P, but in terms of coordinates, this is what? Let's see, x2 minus x1 and y2 minus y1. This is now a vector. And so the notation here, and this is important also to talk about, we have vector u, which can be written like this, u1, u2, or v, well, or I'll write another way. Sometimes people will write vectors like this with this kind of bracket. Sometimes people use this bracket to distinguish it from a point, but every point corresponds to a vector, as I will about to discuss. So what is this and what is this if you think about it as a vector? This is what is the vector. This I'll say is. So this notation, this is the vector with head at the point u1, u2, and tail at the origin. And when you have, so a vector of this form, meaning its tail is at the origin, is called, oh, here's how I will put it, this meaning underlined, in this form. This is sometimes called its position vector, a position vector, or it's thought to be in what's called standard position. And this is really what we were thinking about when we were doing motion in space, and we had a P of t equals, right? It'd be t squared, square root of t, e to the 2t, I don't know. And then 3 components. Right here, I'm just talking R2 here. But the same applies in 3 components. What you're really thinking about is you're thinking about the particle as being a point moving in space, but really the vector starts at the origin and ends at that point. So the whole time this particle is traveling in space, you can think about a vector following that particle around that begins at the origin and ends at that point. And frequently, sometimes, as I mentioned, you'll use this to distinguish the vector from the point, but frequently we use this notation for both the vector and the point because we will go back and forth between either the point sitting in Rn and a vector which begins at the origin, has tail, I don't know why I started to confuse myself, has tail at the origin and head at that point. Those are, we go back and forth all the time between those two. Okay, so when you're in this case, it's standard position, and you can go from a vector with any head and any tail to one in standard position, just like this. Okay, now let's do an example of this. Let's take P to be the point -3, -1, and Q to be the point 2, 4. And let's just sketch the vector PQ, and we will find its position vector, I'll say corresponding position vector, and length. And this is where I will remind you the formulas that we know about length, which we have discussed already when we were doing distance traveled. Now, let us sketch the vector PQ. This is our first step. This is the tail, and then 1, 2, okay, 1, 2, 3, 4. This is the head. Okay, so then we just there it is. Okay, PQ. Like this. Very nice. Well, let's find the position vector and length. Okay, this is not too terribly hard. So PQ, you see, this is not in that form, but we can just take, well, the y component would be 4 minus minus 1, which is 4 plus 1. The x component would be 2 minus minus 3, or 2 plus 3. We get 5, 5. This is the vector, which means if we picked it up and shifted it so that the tail was at the origin, the head would be at 5, 5, and we would have the exact same vector. Now let's find the length of this vector. Well, let me recall that if you have some vector, let's say v is x, y, then the length of v is the square root x squared plus y squared. And similarly, if we were in 3 dimensions, if we had x, y, z, then the length would be the square root x squared plus y squared plus z squared, like this. This we have done. In any case, here, the length of PQ, this is the square root of 5 squared plus 5 squared. This is the square root of 50, which is, let's see, 5, the square root of 2, like this. So this is the length of this vector. Okay, so now we have u is, I want to think about vector addition, subtraction, scalar multiplication in terms of these components. And this really should be review for you based on the kind of things we have done in class. Because we have had to do more than this. We've had to integrate. Say, velocity functions, which had 3 components as a vector. But if we add u plus v, if we subtract u minus v, or if we multiply by a scalar, let's say c times u, this is all component-wise, meaning we add first components, u1 plus v1. We add second components, u2 plus v2. And this is really thinking, so I am adding 2 vectors in standard position. So these are vectors that have their tail at the origin and their head at point u1, u2, for example. And then we subtract, component-wise. And we multiply component-wise, okay? And we also know, because of what we did in class, we integrate, we differentiate component-wise. It makes vectors very nice to work with because so much is component-wise. Okay, so let's do an example. There are a few examples. Where am I in my notes? Okay, here we go. Let's take u to be 4 minus 2 and v to be minus 4, 6. And let's just calculate as an exercise in this the length of 2u plus 3v. And then we have a few more things to do in this lesson. Well, first, let's do this. 2u plus 3v equals, well, it's 2 times this vector plus 3 times this vector, which everything is component-wise. So this is a vector where my first coordinate is 8, minus 12. Maybe I will do that in 2 steps. And my second component is minus 4 plus 18. And this equals, if I just add, I have, oops, this should be a plus, excuse me. 8 minus 12. Okay, very nice. This is minus 4, 14, like this. Now then we want the length, so we practice the length of 2u plus 3v. This should be a number, right? Not a vector. This is the square root of, well, it's minus 4 squared plus 14 squared. This is the square root of 16 plus, 14 squared is 196, which is the square root 196 that I had to look up, which is the square root of 212, which maybe I won't worry about simplifying. What do I want to talk about next is the concept of a unit vector. This is a quite important concept in Calc 3 or in vector calculus, is that of a unit vector. A unit vector. This is just a vector with length 1. Okay, it can have any direction, and it's a unit vector. Now, let's take any non-zero vector. Oh, I'm going to call it v, because sometimes we refer to u as a unit vector. So let's just start with v. V is going to be a non-zero vector. Then, if you take v and you divide by the length of v, this is a unit vector in the same direction as v. In fact, some will even refer to this as being the direction of the vector v, because you can think about, if you think about only having a direction, let's just think about in R2, although this definition certainly works in R3. If you think about the unit circle here, so this, if you think about the unit circle in R2, every possible unit unit vector, excuse me, you can draw with the tail here and then the head here, ending on the unit circle. And you will get every single possible direction, right? So in a sense, this unit vector, which you take v divided by the length, is really the direction part that comes up in the every vector has a direction and a magnitude. Okay, that was just a comment. And certainly, one more comment, certainly this has length 1, because how we even started defining scalar multiple of a vector, this would be defined to be the vector with direction same as v, because 1 over the length is a positive number, and its length would be the length of v times 1 over the length of v, right, which is 1, like this. Okay, so let's do an example where we do some calculations here, and then I will make one quick comment. Okay, so let's take P to be 2, 6, and Q to be 3 minus 4. We want to find, okay, this is going to be exciting, 2 vectors. We'll have to think a little bit, parallel to this PQ with length 3. That says 3. or with magnitude 3? Well, the first thing we need to do is figure out, so you see, this is not just compute a vector, find the length. We have to do something. We have P, we have Q, 2 points in the plane. And now I want to, first of all, I find the vector PQ, but then I need to find 2 vectors parallel to it, which means there'll be scalar multiples that have this very specific length, 3. Okay, first let's find this vector. Well, -4 minus 6 is -10, and then 3 minus 2 is 1. This is PQ. How am I going to do this? Well, here's my strategy. Move that back a little bit. First, I'm going to find a unit vector. Here, I'm going to take PQ over the length of PQ. This will be a unit vector in the same direction. And then just multiply that by 3 and minus 3. And this will work. So let's do it, and we will see why. Okay, so the length of PQ is the square root of 1 plus 100, square root 101. And that doesn't sound, I'll just leave it like that. Okay, so then if I take the vector, which is 1 over, maybe I'll write it in the denominator here. If I take 1 minus 10 divided by square root 101, this is a unit vector, right? This is unit, and it points in the same direction as PQ. All I've done is scaled, divided by the length. Well, now I want to construct 2 of length 3. So I can take this and multiply by any number. Let's say non-zero. And I will get a vector that's parallel to PQ, right? Because this is. So one of them, so my answer here, my first vector is just multiply this by 3. We know the length will multiply by 3. 3 times something of length 1 will be length 3. So the first answer, maybe I'll write it all in parentheses, would be 3 over square root 101, and then minus 30 over square root 101. This is one answer, and the other one, if we want a different vector, well, just take the same thing, but in the opposite direction. So that we would have minus 3 over square root 101 and 30 over square root 101. Or another way to think about this is just multiply this unit vector by minus 3. Now, before I do anything else here, let's just check, because it's a nice exercise to check that in fact we have, well, the length calculation for both of these will be the same. Maybe I'll work with this one. Let's just check that the length is 3. It should be based on our construction. I started with a vector divided by the length, that's unit, multiplied by 3, should give me length 3, but it's also a nice activity to check. This would be the square root. We would have 3 over square root 101 squared plus minus 30 over square root 101 squared. This is a square root. We have 9 over 101 plus, we square this, we get 900 over 101. This is 909 over 101, which is 9. We in fact get 3. And let's see, I worked with this one. This one would be the identical calculation, because you put a minus here, and then this would be a plus, but you square it, and we get the same thing. Okay, so in fact, the length here is 3 of both of these, and because they are a multiple of PQ, or scalar multiple, they are both parallel. Okay, very nice. Now, I only have one more thing to talk about in R2, then I will spend just a few moments talking about R3, because really almost everything I've done works also in R3. So there are two important unit vectors in R2. And they are the following. One of them is written I. This is the vector 1, 0. The other one is J. This is the vector 0, 1. Now, if you think about these in R2, in fact, I will use this picture in a moment. If you think about them in R2, let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I and J are just sitting on the axes and unit. So this is I here, and then pointing up is J here. Maybe I'll put the little hat on top. The hat on top. Okay? Now, every vector in R2 may be written in terms of I and J. Every vector, and this is one reason why they're so important, every vector in R2 can be written, in fact, can be written uniquely. Maybe I'll just say can be written in terms of I and J, and I'll show you it's not that hard to think about per se, but if we take, for example, let's say 5 minus 7, well, we can do this algebraically or geometrically. Let's do it both ways. This is 5, 1, 0, minus 7, 0, 1, which is 5i minus 7j, okay? If we think about this here geometrically, and this goes back to our discussion of adding vectors. Okay, let's do it. Well, what's 5i? 5i, you stretch it, right? Or this is an integer, I just add I to itself, 1, 2, 3, 4, 5 times. To here is 5i, okay? And then minus 7j, oh goodness, I'm going to go 1, 2, 3, 4, 5, 6, 7. It's going to be all the way down here. I'm drawing this like parallelogram rule, although I certainly could have put it here and done triangle rule. Minus 7j points in the opposite direction, has the length 7. 1, 2, 3, 4, 5, 6, 7. Okay, good, is here. And then, well, this extends, and in fact, 5i minus 7j, thinking about, this goes back to how we started thinking about vectors, would point here, okay? And this is 5i minus 7j. But you notice here that this point it ends at is 5 minus 7, okay? This is exactly what we see here algebraically, but it also works with the geometric picture. Okay, now, briefly, let me just mention R3, okay, because not much changes in R3. I will make only a few comments. Okay, so in R3, well, first of all, we have 3 coordinates, and let me just say that the x, y, z coordinate system, this is what's called right-handed, and I will discuss that in a moment. But what are these well, we have 3 important unit vectors such that we can write every vector in terms of all 3, which we will frequently. They are I, which is 1, 0, 0. They are J, which is 0, 1, 0. But then we have a third one, which is K, which is 0, 0, 1. Okay, so you think of them as this lies along the x points forward on the x-axis, this points forward on the, well, I don't want to point up on the y-axis, and this points forward on the z-axis. But what do I mean by right-handed? Let's take your right hand, and I always have to do this to figure out which is which. It's this one. Okay, my hands have marker on them, but in any case, I'll turn this way. So if this is I, your pointer finger, and this is J, your middle finger, then which way your thumb points tells you K. So this says this is how this coordinate system sits, I, J, and K. You see, it wouldn't work like that if you tried your left hand, because you would have I, J, and K would point down, and it doesn't do that. So it's right-handed, which means if you draw here right-handed in the plane, the x-axis comes here, the y-axis frequently will be here, right, I, J, and then the z-axis points up like this. Gives us an ordering of these coordinate axes. Okay, so this is, this is supposed to be z. This is the right-handed aspect, like this, okay? I, then back here, J, K points up, okay? This is the coordinate system. And then, what else do I need to say? Well, if we have scalar multiplication, if we have addition, if we have subtraction, this is of vectors. These are all component-wise, just as they were in the two-dimensional case. And the only thing that really changes is the length. If you take the length of a vector, let's say u1, u2, u3. So I have this written sort of in standard position where the head is here and the tail is at some point u1, u2, u3. Okay, so you think, just like in 2D, you think of points in the plane, and here it's points in space. You can think of them as being vectors in standard position, where you start at the origin and then with the tail and the head ends at that point, or you could also think of it as a point. But the length of this vector is, just as we had in our, what was it? Distance. It's u1 squared plus u2 squared plus u3 squared, like this. This gives you some of the algebra in 3 dimensions. It's really the same as the two-dimensional stuff we were talking about.